Hi. In the previous lecture, we have discussed about the static service drive. In this static service drive, this is the circuit diagram for that. Actually, you have induction motor, you have converter or rectifier, inverter, and transformer, uh, and all the things we have discussed. We are going for the closed loop control of static service drive. So, we talked about the resistive control. That time itself, we were telling why we are coming to the static control. So static control is actually done for the automation of the system. So here also it is a static system. So we can now make the automation, and that automation also you can control that with a controller. Mm, that method is described here. So we are going to discuss the closed loop control of static service drive. So closed loop control is mainly intended to control the drive internally with certain or some uh, parameter input. Like if you want to control the speed, you are giving the omega m star, that is your parametric input or reference input. So according to this, you have to control the whatever the speed you are giving here, you have to get as an output from your induction motor. That is the main motive or main aim of closed loop control of static service drive, or that is the main motive of closed loop control. So here we are going for the static service drive closed loop control. As you can see here, this is your rectifier, and this is your inverter circuit. So I have just shown in a block, and here this is the id is the current which is passing, or this is your rotor current which is passing from after your rectification to the inverter. So we have discussed how we have calculating omega pg, and from pg, omega pg is actually we have taken it from the output vd and id. So here, so vd means vd1 and vd2, vd1 here and vd2 here. We are equalizing that, then only we were discussing about all the things. So that we have discussed in the previous session. So now we are going for how we can implement the closed loop control in static service drive. So before going to the closed loop control, wherever you need a control, you have to make some measurements. So we will check what are the measurements here. Here we are having a speed sensor as or taco. You can call it as a taco. Taco is there are lot type of tacos, digital tacos, which counts the rotations, or analog tacos, which if you are directly connecting that to your rotating part, it will generate, it will act as a or it is a DC motor, and it will do DC generator, and it will generate some voltage. That voltage is taken as the omega m signal. So that is the speed sensor. If you are using a counter, then you will be getting if you are according to the count, we can calculate the omega n p with certain equations, like that depends upon the counter which you are using, and how many counts you are making in a rotation. Like if you have 1000 counts per rotation, then 1000 if it is counted 1000, then it will take as a uh, one rotation. And if you want to calculate the rpm, that one rotation, whatever the time is taken, uh, that will make give the speed. Okay, from that information you can calculate the speed omega n. So this is the speed sensor, and another sensor we are having is a current sensor, ID. We are sensing the ID. So why we are sensing the ID, that also we have to discuss. We have certain static devices here. So there should be some limit for ID. If it is increased beyond that, then it will the system will fail. That is why we are finding the ID, and we have to control the ID also according to the speed. Okay, so here the transformer, already we have calculated the value of m, that is 1 is to m, which is the turns ratio of transformer. So the whole system I have discussed. Now we will be going for the control of static shift distribution. In the, when you are going for the control, you have sensed the speed omega m, and you have given the reference speed omega m star. So this is an adding block. Here omega m star minus omega m, and error signal will come here. You can see here, if omega m star is greater than omega m, or you have to accelerate the drive, then your error will be positive. And if you want to decelerate the motor, then omega m will be greater than omega m star. So the error signal will be negative. uh, so if you want to decelerate, error signal will be negative. So if you are giving this to the speed control controller, maybe PID or PD, whatever it is, or sometimes it will be a neuro system, fuzzy system, or any other system, like in control system itself there are a lot of type of controllers, rather than this PID. So any controller which you are keeping here, the selection will be according to the characteristics what you need in the output. So if you want accurate, then we will be going for PID. So if you are going for PD, then there will be an offset. If we are going for PI, then offset will be 0, and in the PI, the time required to reach the steady state will be greater. That all we have been studied in the control system part. So just I am going to give you an idea of the control of the closed loop control. The speed controller will take the error signal, and it will process, and it will give an current signal. Like for the speed, if you want to increase the speed, what current should be obtained here? That signal the current controller will give. This depends upon the design. Whatever you are giving the design, according to that, it will give an ID star signal. And we have a current limiter here. This current limiter is given because if you have certain limit for this current, or I previously I said, if you are increasing the current beyond ID, then there is a chance of failure. So we have to limit the current. That is why we are using a current limiter here. So here in this current limiter, if you have given the ID star, then it will limit the current and it will give here. So already you have measured the ID, and ID star is we got it from speed control. I will tell it is we have obtained this ID star from speed control. Even we have a current limiter here. So now you are having ID star and ID, so you will be getting an error here. This error signal will be given to the current controller, and this current controller also will process same like PI, PID, whatever controller you are using. It depends upon the characteristic of the output you needed, and so if you are taking the output, this current controller will give the output to the firing cycle. Actually, this current control will give a signal which will decide the firing angle or firing angle which required for your inverter. So alpha, it is usually in between 90 to 165. Why 165 we have discussed previously. Actually it is 90 to 180 for because of the commutation requirements or commutation problems, we have reduced to 165. So this signal is given to the firing circuit, and the firing circuit will give a signal which will make firing angle alpha, and the signal is given to the inverter, and this inverter will uh, provide the voltage here VD, and it will invert the whole current to AC, and it will fed back to the supply. And uh, when you are controlling the alpha, this VD2 has been changed. So according to the VD2, your power omega PG, SPG has been changed, and this change will reflect on the speed. That also we have discussed previously. So this is the closed loop control of static Sherbi drive. In the next, we will go to the static Kramer drive, which is the second type of speed control method, with the slip over recovery scheme. In the slip over recovery scheme. Thank you.